All right, let's go ahead and take a look here at example A. Now, I want to highly encourage ourselves to not just passively watch me solve this problem and then think, oh, I can follow that, I can reproduce that. All right, I think we've talked about this before. But it's very different to watch someone who knows what they're doing do something than to reproduce this on your own, right? I am fully aware that there has been a pretty big step up in difficulty from 3.3 to 3.4, right? I know, right? That's why we're doing as much practice as we're doing. It's so that we can kind of refine these motor skills so that we can do well with this. This is not easy. This is, I would say, probably one of the difficulty spikes of this course in general is what we're doing here in 3.4, right? And so when we are presented with a bell work and when we are given 15 minutes to work at the start of that class on that bell work, and when we make the choice not to take advantage of that, you lose a lot of my sympathy. Like a lot of it. And so again, you can't just passively engage with this material and expect to master it. You have to try, and you have to get feedback on your efforts, and you have to try and reproduce what I am doing and see where the gaps in learning are, see where the gaps in understanding are before you can truly appreciate whether you could do this on your own. Because I will tell you right now, I will be super upfront with this. This question, A, and also, honestly, probably something like B, not this exact question, but certainly a question styled like it, will 100% be on the test that you guys have in a week. It'll be either number 2 or number 3. Right? Beyond a shadow of a doubt. You will need to do this, if not beyond the scope of this course, you'll need to be able to do this a week from today. And so I should say that, and that should mean that everyone knocks this out of the park, because we've done 3 examples of this in class. We're doing an additional example as bell work. I'm going to show you 2 different ways to do it here as bell work. This should be free points. Free points on what is probably computationally one of the harder problems that we have done. You know it's coming. I'm telling you right now, you now need to practice it to the point where you can do it perfectly. Right? Do not engage with this class passively. You are going to either trick yourself into thinking that you understand something when you don't, or you're just going to accept that you don't understand something, and that's also just silly when you know exactly what is coming. All right. So let's take a look at this. This is 3 to the x plus 2 is equal to 2 to the 3x minus 4. We have 2 different strategies to approach this. We have the one that we looked at on Monday. We have a new one that we introduced yesterday. What was the first strategy that we looked at on Monday? What was that very first thing that we did here in order to solve this? Okay, so first strategy was changing the base so that the bases on both sides match. Why was that a strategy? What am I able to do as soon as the bases match? We get to drop them. We get to set the exponents equal to one another, drop the bases, and then as soon as we have the exponents set equal to each other, we're good to go. Then it's just an algebra problem, right? And that was using the one-to-one property, right? B to the x equals b to the y implies that x must equal y. What was the other strategy? I see something here in the exponent. I am trying to solve for something in the exponent. And so how do I get into my exponent? How do I access the exponent there? Yeah, so we could rewrite this statement, this exponential statement, as a logarithm. And that also works. And either way is fine. We're going to look at both, but either way is fine. Let's start with rewriting the base, because this is kind of how I introduced us to this problem style of rewriting the bases so that they match. Does it matter which side I pick to match to? No. Do I even need to match to one side in particular? No. I could write this in base pi if I really wanted to. I don't know why you would, but you certainly could write this in whatever base you want, and it should still work. The only important thing here is that our bases match. All right, but if we want to be clever about this, then it would probably be smart to only have to change one side of our equation rather than having to change both sides of our equation. So let's pick a clever base to match to so that I only have to change one and not change the other. What would a good candidate base be for that? I like 3. I would say 2 would be another smart one. If I choose 3 as my base, then notice that I only have to change the right-hand side of my equation because the left-hand side already is in base 3. If I choose 2, I only have to change the right-hand side of my equation because the left-hand side is already in base 2. Or whatever, you get it. One of the sides is in base 2, one of them is in base 3. You understand. For the sake of this demo, let's turn 2 into 3. So I am going to focus on the right-hand side here. Okay. So I am trying to write 2 as 3 to some power. What is the power that I'm going to raise 3 to in order to equal 2? 3 to the log base 3 of 2. This is the hard part of this problem, all right? If there was an easy way for me to help you remember this, then I would have said it a long time ago, right? I've spent most of my time trying to convince you that this statement is in fact true after writing it. That does not make it easy to reproduce. This is not an easy problem. It's just a thing that you got to be able to do. If you still don't understand where that comes from, that is okay. Stare at it until you're able to reproduce it yourself, right? I want you to have the conceptual understanding of what we're doing, because what we're doing here is using the identity property of logarithms, that second identity property, in order to rewrite 2, and you can do that with any number, but you don't need that conceptual understanding to be able to reproduce this. There are very clear patterns at work here. Learn the pattern and be able to reproduce it on your own. All right. Now, we're not just changing 2, right? In particular, we want to change 2 to the 3x minus 4. But we now have a new way to write 2. We are going to take this, what we see here. This is just the same thing as 2. We're going to say this 2 here. We're going to replace one with the other. This is 3 to the log base 3 of 2 raised to the 3x minus 4. Still haven't touched the left-hand side of my equation yet. We're still just working on making the right-hand side look like how we want it to look. Base to a power, what do I do with those powers? Multiply them. This is 3 to the, I'm going to do this in parentheses here, 3x minus 4 times log base 3 of 2. I think a lot of people see log base 3 of 2 and they get really scared. That is a number. It's about 0.63. That's all it is. 0.63 and some change. It is an irrational number, so we're not able to actually simplify it down to its decimal. We're going to leave it as log base 3 of 2. But it's just a number. We can treat it like it's a constant. Okay, so I get that 3 to the x plus 2 is equal to 3 to the 3x minus 4 times log base 3 of 2. Why did I do that? What was the point of any of this? So that I can drop the bases. Base to a power equals base to a power. I can now set the powers equal. X plus 2 is equal to 3x minus 4 times log base 3 of 2. And now it's an algebra problem. Is it a particularly easy algebra problem? No, but it is still just an algebra problem. We have an expression of x. We're just trying to solve for x here. I've got x on both sides of my equation. What do I need to do to solve an algebra expression where x is on both sides of my equation? Get all my x's on one side and everything else on the other. All right. In order to get all my x's on one side, I'm going to need to fix these parentheses here. So we're going to distribute the constant log base 3 of 2 into these parentheses. So this is x plus 2 still equal to 3x log base 3 of 2 minus 4 log base 3 of 2. Again, these are just numbers. 3x log base 3 of 2 is pretty close to 2x, actually. It's pretty close. And 4 log base 3 of 2 is what? That's going to be close to like 3.5 or something, maybe. Yeah, close-ish. I guess close to 4. Yeah, whatever. Close to 3. Regardless, we now have to figure out how to get all of my x's on one side, all of my not x's on the other. You can do this a variety of ways. The way I would do it, just to make things easier for myself, I'm going to subtract x from both sides, and I'm going to add 4 log base 3 of 2 to both sides. Just to make sure I don't have a bunch of minuses floating around. Let's just resolve that. So what do I end up with? Well, I end up with, on my left-hand side, 2 plus 4 log base 3 of 2 is equal to 3x log base 3 of 2 minus x. So all of my x's on my right-hand side, all of my not x's on the other. You could have done this the other way. You should end up with the exact same thing. Normally, we would combine like terms. Right, after we do that, normally we would do like the 3x log base 3 of 2 minus x. That would actually simplify to something meaningful, and we could combine like terms and just be happy. In this case, our numbers are too messy for that. We can't actually combine like terms. We're going to have to settle for something else. How do I deal with my right-hand side? How do I isolate x when I'm not able to combine like terms because my numbers are too messy? We're going to factor an x out to the front. Bring an x. This is 3 log base 3 of 2 minus 1. 3 log base 3 of 2 minus 1 is just a number. It's pretty close to 1. It's like 0.9-ish. And so I have a number times x. What am I going to do to solve for x? Divide both sides by that number. It's a messy looking number, but again, still just a number. Divide 3 log base 3 of 2 minus 1. And so what do we get for x? Well, I get that x is equal to 2 plus 4 log base 3 of 2 divided by 3 log base 3 of 2 minus 1. Could you have done this exact same process and gotten something that looked completely different? Absolutely, you could have. If you had changed bases from, instead of making the bases all be 3, if you had made the bases all be 2, you would get something that looks similar, but that is different. And that's okay. So here, the important way to check yourself is, did you do each of the steps that I did? And if that's logically consistent, then you're probably good to go. If you're checking yourself at each step, you're like, okay, I did this. Doesn't look quite right. It doesn't look quite what you did. That's fine. I did it. I did it. I did it. It's fine. There are an infinite number of ways to write this exact number here. And this is just the one that we stumbled upon. Do you have a question, Keenan? Okay. Yeah, okay. Can I check? Sure. This looks good. This looks good. So adding and then subtracting x. And then don't forget the minus x on this side, and then you're going to factor out that x and then divide. Okay. That looks good.
What I do have a question now.
Yeah.
So what are you subtracting the minus x from? Is it from x plus 2?
From both. So if I subtract from this side, I also have to subtract on the other side. Think of this as moving my x over to the other side. So I get 0 x's over here, and I get a mess of x's over here.
What if that was like something like 2x?
You just subtract 2x from both sides.
Okay.
Yeah. However many x's there are over on this side, subtracting them over to the other side. Grouping all of our x's onto the other side of the equation.
With the denominator, you just that is log base b, so okay.
Yeah, you can write that as obviously okay. Yeah, there's certainly maybe a little bit of cleanup that you could do for like writing in various different forms. You could write this as 2 plus log base 3 of 16 on top and log base 3 of 8 on bottom. That's totally fine. I do not need you to. You can leave things like this. This looks fine. But you certainly could. And it would be correct if you did it well. Is my claim that this is easy? Absolutely not. This was a full page of work for this one problem. Okay, maybe not a full page for you guys, but like a full page, on my end. That's a lot of work for one problem. It's a lot. This is not easy. Which is why we've now looked at it 5 times. Okay, so that was the method that we looked at on Monday. But we have a new method, which also works, which is also just as fine, that I think some people find easier, which I think is fair. It takes what I think is the difficult step here, this first step here, and eliminates it, which is nice. And that is taking our exponential expression here. This is 3 to the x plus 2, 2 to the 3x minus 4, and we are rewriting this as a logarithm. So what is the basic idea here? Well, in this case, we have b to the y equals x. We're saying, well, I want to know something about y. I want to know something about the exponent. So we're going to rewrite this as y is equal to log base b of x. I want to note that this x here is not the same as this x up here. Right? I am simply using x, y, and b here as we did with our definitions of what logarithms were, just to help us keep our head wrapped around what goes where. And in fact, maybe instead of log base b of x, or log base, maybe instead of log base b of x, maybe it would be better to say b to the power of a equals c, implies that log base b of c is equal to a, just so we don't get confused with like the x's that I'm referring to. If you're able to keep straight in your head what is the variable that we're working with and then what is like a blanket little substitution trick that I'm using, then that's fine. But I think that this is a nice way to do it, just so we don't get confused about x showing up twice. All right, so if our equation is this, b to the power of a equals c, then I claim that there are 2 possible values for b that we could use, both of which will give us different logarithms. What is one possible value of b that I could use? I could use 2. So if b is equal to 2, what is my power? What is a going to be equal to? 3x minus 4. And what is c going to be equal to? Exactly, 3 to the x plus 2. This is a totally viable way to define what I have written here. What is my other way that I could do this? What else could b be? I like 3. Okay. If b is equal to 3, what is a going to be? X plus 2. And c is going to be 2 to the 3x minus 4. Very good. If you can just go straight from looking at the exponential into the logarithm, you don't have to show all of this. I am just doing this so that we can kind of keep track of the pieces because it is a little bit complicated. This is a little bit of a complicated statement to turn into a logarithm. All right, so we're taking these pieces and we're really just plugging them into our definition of a logarithm right here. So for my first set, for the first way I have defined b, this is going to be log base 2 of what? Of c, so this is 3 to the x plus 2, is equal to a, which is 3x minus 4. Or what could I have gotten? Well, I could have also gotten log base 3 of c, this is 2 to the 3x minus 4, is equal to a, in this case, that x plus 2. Both of those are completely valid. And then what can I do with my first example, that x plus 2, and my second example, that 3x minus 4, that are living in the exponent of my logarithm? Power rule, drop them down to the front. This is x plus 2 times log base 2 of 3 is equal to 3x minus 4, or 3x minus 4 times log base 3 of 2 equal to x plus 2. And from here, it's the exact same problem that we just solved. In fact, it's literally the exact same problem. Notice that what we have here when we did log base 3 is exactly what we see right here. Those are, in fact, the same equation. So two methodologies, two possible methodologies, I would say. Really, there are 3. There's one that I'm not really talking about because it's not really goal-oriented. I prefer kind of talking about these goal-oriented methodologies to help us, like, if I'm just looking at this and I haven't memorized steps, how can I figure out what to do? First goal would be for what we did here, matching the bases to use the one-to-one property. I match the bases to drop the bases. That's one goal. Another goal, what we did here was noticing I want to crack open the exponent. I want to get into the exponent to talk about the contents of the exponent. What kind of function talks about exponents? Logarithms. Taking our exponential, rewriting it as a logarithm to get into that exponent. And those are both completely viable goals that will lead you to the same conclusion. Yeah, right. Look at how to solve the x plus 2 one. You want to check your answer? Let's see. I was able to do it in my head last time. Let's see if I can replicate that. That's gonna be 4. So I get x is equal to 4 plus 2 log base 2 of 3 divided by 3 minus log base 2 of 3. That look about right? You might have done it in a different order. You might have the bottom be negative and the top be negative, and that's fine. You get the exact same thing. Yeah. Yes. No. That is. I didn't do anything simplifying. No. You need to solve for x. So you need to get the x's on the same side, factor out an x, divide. So what we have here is not the solution. This is the start of the algebra step for this. And if you had wanted to, you could have written these both as e to various things, and then you would get a whole mess of ln's in your end result, and that's fine, and that works. That's totally okay. Yes, Gabby. Yes. Actually, the ending for this one should be exactly the same as what we see for here. Yeah, it should be exactly the same. Now, if we were to solve the left-hand one, notice that what we get here looks different than what we got for our first way that we solved it. But if you plug those into your calculator, they are in fact the same value. They should work out to be the exact same value. They're both correct, yes. That's the fun part of this for me, is that I have an infinite number of possible correct solutions that I get to parse through to make sure that you have in fact done this correctly. So there are an infinite number of ways that you could write this number correctly. These, I would say, are probably the two most concise ways to do it. But there are others. All right, let's take a stab at B. This is ln of x squared minus x minus 12 is equal to the ln of 3 plus the ln of 2x plus 2. Just like with our exponentials, we have the exact same ways to solve our logarithmic equations. Either we can use the one-to-one property. So that says if I have log base b of x equal to log base b of y, that x must equal y. Well, that is possible. And in fact, I would probably recommend that for what we have here, just because it's set up with the ln on both sides. We're already kind of primed for this. And then the other way would be to do what we did in this previous example, where we are trying to access the contents of our logarithm. Let's rewrite this as an exponential to isolate the inside of our logarithm. That would also work. Either way is fine. And again, just like the other one, you can do either, but this one's really well primed for doing the one-to-one property. In order to use the one-to-one property, though, I need one logarithm of a single base on one side, one logarithm of the same base on the other side, which is not currently what I have. In particular, notice that on the right-hand side of my equation, I have two logarithms. I am going to need to condense those so that I can kind of work forward from here. So what could I do to combine the two logarithms that I see here into one single logarithm? Product rule. So what is that going to look like? ln of 3 times 2x plus 2, which will be the ln of 6x plus 6. What's the point of that? Why do we do it? Okay, I want to be I'm going to be very persnickety here about our choice of word with cancel. Am I dividing both sides by ln? No. Can I divide by ln? No. ln is a function. Dividing by ln to cancel ln would be like dividing by squared to cancel squared. It doesn't make sense. You can't do it. Right? What do we do to cancel squared? We use the inverse function. Right? We compose it with the square root. It's its own separate little thing that we're doing to undo squaring. Same thing with ln. We can't just divide both sides by ln. Ln divided by ln is not a number. It's not 1. It's nonsense. Don't write it. All right, it's gobbledygook. I don't want to see it. It'll make me very sad. Don't divide by ln. It's not what's happening. What are we doing? We are using the 1-to-1 property to drop the ln's. So it's not really canceling per se. We're using the fact that if the ln of these numbers are equal, then the contents themselves must be equal. So therefore, x squared minus x minus 12 should be equal to 6x plus 6. And now we have a quadratic. And the good news for us is that we are experts at solving quadratics. And if we weren't experts yesterday, then we went home, like I said, and wrote down the quadratic formula 50 times. And so we are now experts in the quadratic formula. Good news is, though, this one's actually factorable. It's not too bad. We have to offset from 0. So this is going to be x squared minus 7x minus 18 equals 0. What are two numbers that multiply to make negative 18, that add to make negative 7? Negative 9, positive 2, you'd split the negative 7x, blah, blah, blah. We've seen that a bunch of times. You're going to get x minus 9 times x plus 2 equals 0. And so what are my values for x here? Negative 2 and 9. Am I done? No. What do I need to be very, very careful of? Extraneous solutions. Do these give me a negative inside my logarithm? Let's try. Let's plug in negative 2 first. I do the ln of, I would probably do the simplest one, so like 2x plus 2 is probably the simplest one. When I'm plugging in 2, or negative 2, I'm going to get ln of 2 times negative 2 plus 2. This is the ln of negative 2. Is that okay? No, that is not okay. That means that negative 2 is not a solution. All right. Not that there was anything wrong with what we did to get negative 2. It just doesn't work as a solution. We plug it back into our original function. It breaks our original function. We can't have it. All right. What about 9? Let's try 9 here. This is the ln of 2 times 9 plus 2. I get the ln of 20. Is that okay? Yeah, that's totally okay. 20 is a good number. And then I get the ln of 9 squared is 81 minus 9 minus 12. I get the ln of 60. Is that okay? Yeah, that's perfectly okay. And so 9 is a solution. In fact, it is the only solution to this equation. Yes, Don. So if you were to factor out the other side for the purpose of like maybe splitting apart with product rule, it takes you further away from your goal as getting 1 at logarithm equal to 1 logarithm. So there's nothing wrong. You can factor it out x minus 3 or x minus 4 times x plus 3. It's just, it's hard to then move forward with that. Basically, yeah. In particular, quadratic equals 0, so that you can then use the zero product property. Yeah. All right, questions here? Yes, Oliver. So ln of -2. So what power could I raise positive e to in order to equal a negative? There isn't one, therefore it doesn't exist. Yeah, so you can only ever plug in positive numbers into your logarithm because you can never. So the logarithm tells us the power that we have to raise the base to get the content of the logarithm. And we're never able to take a positive base, raise it to a power to get a negative, unless that power is a complex number, and we're not dealing with those. Yeah. So it is technically possible, but it's not possible for us, and so we will just leave it be. Good question. What else are we can't have negatives inside of our logarithm. What else are we not allowed to have inside of our logarithm? We're also not allowed to have 0 inside of our logarithm. Similar reason, power or a base to a power equals 0 can't be solved. There's no power that you can raise a base to make it 0. Unless that base is already 0, in which case we're not even, like, that's just not even a consideration. Our b is not allowed to be equal to 0. All right. So today and tomorrow, we're going to be looking at some application problems for our logarithms. Like I kind of implied, this is really where we are going to see a lot of application just in general, is with exponential functions. It's just what we got. First thing that we are going to be looking at today, tomorrow we're going to focus on the other one, but today we're going to be looking at half-life problems. What is the half-life? What do I mean when I'm talking about half-life? Yeah, Hen. Yeah, exactly. So this is an amount of time that it takes for a radioactive element to decay, and not really the element itself decaying, but like an amount of radioactive substance to decay down to how much should be left? If it's half-life, half of what the original amount was. So we could think of the half-life as being how long it takes to either decay in the case of half-life. If I'm grouping half-life and doubling time together, doubling time is just the opposite. If we are decaying for half-life, then we'll be growing for doubling time. Decay or grow to half or double of the original amount. Okay. Now, whenever we are talking about radioactive growth or radioactive, not radioactive growth, that'd be crazy, radioactive decay, this process, like we mentioned earlier when we were looking at this, technically speaking, is a discrete process. There is a radioactive isotope. There is a single atom that is unstable and at some point in time splits apart into stable pieces. All right. So it is technically speaking a discrete event. But if we think of the number of atoms of a particular isotope in, say, a single gram of uranium, we're talking about like an unthinkable number of these discrete events happening. There are so many of these kind of fragmentations going on within a particular compound that we treat it like it is continuous. Right, so technically speaking, yes, it is discrete. Functionally speaking, we're going to treat it like it is a continuous process. What was our way of modeling continuous growth or decay? What do we have there? Yeah, this was our PERT equation. P times e to the RT. Now, technically speaking, the PERT equation is very, very specifically about money. In particular, that P, does anyone remember what the P stands for? What word? That's the principal, which is like the amount of money that you are starting with. So there's nothing wrong with it. This is ultimately the style of equation that we're going to use. We're going to alter it ever so slightly just to make it a little bit more general. Rather than using the PERT equation, we're going to say that A of t is equal to A sub 0 times e to the RT. A sub 0 and P are really not different, though. A sub 0 or A naught is just our initial amount. Or a good way to think about it is the amount when t is equal to 0, which is the same thing as the initial amount, but you know, it kind of explains why it's A sub 0 or A naught. Okay, t is our variable, t is time. And then R is going to be that growth rate that we're looking at. You'll see in some books they'll rewrite that R as like a K. I'm just going to leave it as an R because it's the same thing. It's the rate at which we are growing or decaying. All right. So if we are considering our half-life equation, so A of t equal to A sub 0 e to the RT. If I want to talk about the half-life of a substance, in order to find that value of R, what could R possibly be? Let's think about what I would do to the output. So we know that half-life is going to be some kind of time. So we're going to be plugging in some value of t. In fact, I'm going to go ahead and call that specific value of t. We're going to call it t hat, just so that we know it's different from our variable. This is a specific value of t. In particular, this is the half-life. All right, so we're going to plug in t hat. And if this is half-life, how much of my original stuff, how much of A sub 0 should be left? Half of it, right? Half of A sub 0 be left. So when t is equal to t hat, we get 1/2 A sub 0. Again, the only reason I'm replacing t with t hat is just to remind ourselves, hey, this is a specific value of t. This is the half-life specifically. Okay. What do I need from this equation? What am I missing here? What do I need to find? Say again? Okay, so numbers for this kind of stuff. But in it, like specifically, where am I missing numbers? Okay, so we're definitely going to need the R. And A sub 0 could be helpful for certain questions, but for the process of solving for R, do we even need A sub 0? Why not? What's going to happen to our A sub 0 like right away? I have A sub 0 multiplied on my left, multiplied on my right. They are going to cancel. We're going to divide out that A sub 0 kind of right away in order to find R. But we certainly do need to know what is this value of R that we're talking about. This is kind of what we're looking for. What is the R here for a particular half-life? Okay, so I'm going to do that. I'm going to divide out A sub 0. I get that 1/2 is equal to e to the R times t hat, where again, that t hat is just some specific value of t. If the half-life is 10 years, then it's 10. If it's 3 days, then it's 3, but now my units are days. You get the picture. I've got 1/2 equals e to the RT. I'm trying to solve for something in my exponent. What are my two methods for solving for something in my exponent? So we could either match the bases and drop them, which maybe be a little bit annoying. How would I write 1/2 as e to a power? E to the You could do negative log base e of 2. That would work. Or what I would probably do is just ln of 1/2. E to the ln of 1/2 would work, or e to the negative ln of 2 works as well. Which is a good observation, but we're just going to leave it as to the 1/2. So that would certainly work. Or I could do what to this exponential expression? Rewrite it as a logarithm. Either way, you should end up getting that the ln of 1/2, which, as Haddon correctly observed, is the negative ln of 2, that this is equal to r times t hat, where again, t hat is just some value of t here. And so what is my r going to be equal to? Divided by whatever that half-life is. And this works regardless of what my initial amount is. This works, it's only really dependent on my half-life, whatever that specific value of half-life is. We could do the exact same thing for doubling time. Let's have down here, we'll say t hat is our doubling time. What's my setup going to be after the doubling time has passed when t is equal to t hat? How much of my stuff is there going to be? 2 times my initial amount. So this would be like 2a sub 0 is equal to a sub 0 e to the r t hat. And so doing the exact same solving process, we would get that this r here is, rather than the ln of 1/2, the ln of 2 divided by whatever that doubling time is, that t hat. Okay, so this does give us a formula for half-life. We could always use this value of r for half-life. We can always use this value of r for doubling time. This also, though, tells us what we would need to do if we forget this formula to find r. You're going to set it up where, okay, my half-life is this value of t, where my output is 1/2 of my original starting amount, and then you're just going to solve that expression for r, and it should give you something that looks exactly like this. So you can memorize this, that's fine. If you want to, that's your own prerogative. But also you can kind of resolve for it each time, and it's not like it's all that onerous. All right, so let's take a stab at example 1 here. In this case, we are told that cesium-137 has a half-life of around 30 years, trying to figure out how much is going to be left after 145 years. All right, so this is my A of t equal to my initial amount here, which is 200 e to the ln of 1/2, 1/2 over 30 times t, where this is just that value of r that we found, where my half-life is equal to 30, and 200 is just my initial amount. Do we have questions about where this equation came from? Or does this kind of just fitting all the puzzle pieces that we've kind of individually established all together? Because this is just A equals A naught e to the RT, and then we found R for every half-life problem. It's that ln of 1/2 divided by t hat. And t hat in this case is just 30. So what do I do to figure out what's going on at 145 years? Well, that's just replacing t with 145. Want to be a little bit careful with where you're actually plugging that in. That t is in the exponent of e. And if you are very, very careful, 200 e to the ln of 1/2 divided by 30 times 145, I get that this is 7.02 kilograms. All right, for B, in that case, we were given a value of t to plug in, a time to plug in. For B, we are instead given a target output, and we are looking for the time that it would take in order to reach that. So in this case, we know that 1 should be equal to our A naught times e to the k, that k, ln of 1/2 divided by 30 times t. I'm trying to solve something in my exponent. So I have the options of rewriting in the same base, blah, 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 solving, writing as a logarithm, either way. But before I do that, what do I have to do to the exponential piece of my equation here? Say again? We're looking, well, in this case, t hat we plugged in right there. But thinking kind of back to what we did yesterday with example 3. What needs to be true about the exponential part of my equation before I can rewrite things as logarithms or change the base? Can it have anything multiplying into it, anything being added onto it? It needs to be isolated. So we first need to isolate the exponential part of our equation, and then we can rewrite this as a logarithm, blah, 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 blah. So what could I do to solve for the exponential piece of my function here? What do I need to do? Divide both sides by 200 should be it. This is 1 over 200 is equal to e to the ln of 1/2 divided by 30 times t. Rewriting this as a logarithm or changing the base, whatever you want to do, this gives me that the ln of 1 over 200 is equal to the ln of 1/2 over 30 times t. ln of 1/2 over 30 is just a number. So I have a constant times t. How do I solve for t? Divide or multiply by the reciprocal. And so I get that t should be 30 ln of 1 over 200 divided by the ln of 1/2 years. Which you plug into your calculator, this is about 229 years. Dividing 1 equals 200 e to the ln. We're trying to solve for e to the whatever so that we can rewrite this as a logarithm. So dividing both sides by 200. Yeah, Dylan. So what is our base for the left-hand piece? Think of, so we could kind of use 1 over 200 as our base, but that's really not an exponential expression. 1 over 200 is just kind of a number. So we're not really going to be able to tease apart a power there very easily. I think more easy would be to let B be equal to E, to have Y be equal to the ln of 1/2 over 30 times T, and to have X be 1 over 200 is how I would do it. So nothing wrong with having the base be 1 over 200. Your Y would be 1. And then your X would be E to the ln and blah, 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 blah. And then you would use product rule to drop. It'd be messy. It'd be messy. But you certainly could, and you would end up with the same answer, but a lot messier. You don't have to use it. We're using the definition of a logarithm here. We didn't use change of base. Right? Our base was E. Our power was ln of 1/2 divided by 30 times T. And then the result was 1 over 200. We rewrote that exponential as a logarithm. Similar to what we did for example 3 yesterday. With some algebra at the end of it, at the tail end. Other questions? Dylan, if it's easier to see, you also could write 1 over 200 as e to the ln of 1 over 200, and then drop the e's, and that would work as well. Either way is fine. Whichever way is easiest for you. All right. Well, that is where we are going to stop for today.